a chance per unit time. So this rate associated with transition is a chance per unit time. And that's not a probability. It's a probability per unit time. So it's a density. It would be another way to put it, a probability density of infection. So let's suppose that it has the value. Trying to think of different ways to explain this, but if we call this value R, okay, this rate value, okay, it's the rate, the chance that that an event will not have gone off after time t, the probability that it will not have gone off after time t goes down as e to the minus rt. In other words, there's a certain chance per unit time. Let's suppose it's 1%. There's a certain chance per each successive interval of time that it will go off. And as time goes on, it's more and more likely that it will have gone off by that point. It's a memoryless process. This is commonly dealt with as a Poisson arrival. It's the time till the Poisson arrival is 1 over r. We could think of this as sort of the lambda associated with Poisson arrival. So another common letter for this, if we think of it in a queuing context, would be sort of lambda. So there's some chance per unit time of arrival. And so this goes down as that, or the probability that you will have seen it by that time goes up as e to the minus rt. Does that make sense? So it's a chance per unit time. It's memoryless. And just this little chance per unit time, and it's in continuous time. So the point to emphasize here is any logic's abstraction of time is continuous, and it's not just fixed time steps. It's actually occurring sort of in a continuous time, and this event may fire at any number of different points here. Okay. Does that make sense? So as long as you are in that state out of which that transition came, as long as you're in this state out of which this transition came, this rate transition came, you as long as you're in this infectious state, you'll have this chance per unit time of recovering. Now you'll notice a very important property of this is that your average time before hitting this event is 1 over r. Wow, that makes the point well. Yeah. Okay. Thank you. Yeah. We need more help from Matt.
Here.
I lost my marker yesterday.
Thank you. Okay. So if you have a rate of r, your average time until the event occurs is 1 over r. Okay. It's the mean time until it occurs. It can be shown in slides I can give to you which derive it. But you'll notice that's why this rate is expressed as 1 over the average illness duration, because the average illness duration, if it's 10, the rate is 1 over 10 or 0.1. Does that make sense? Mm-hmm. And that will ensure that the average time until transition fires equals 1 over r. Okay. Great question, and I hope that unpacks it. Other questions? Yes. Yeah. Yeah. So what you've articulated there is one of the great motivations for using these models, because they have a requisite flexibility to support capturing those aspects of context And I would encourage you, if you're interested in this, to work on a project which helps, maybe puts down, at least at a stylized level, how you might go about doing that within a model. It is, so good news here is that the mechanics of doing it in the software is not the barrier. In other words, the software has the software, the agent-based modeling approach in general, has the requisite flexibility to allow you to characterize phenomena like that. The theory, often the bigger bottleneck is, in my experience, making sure that we have sufficient theoretical grounding for how these influences might take place that we wish to capture in the model. Now, if you can articulate a theory, as it were, for how social influences might affect an individual, or how environmental influences might shape risk behavior, then capturing it within the model is not going to be a big challenge if you have the right set of skills in the team. That's not going to be the issue. It's often developing that crisp, plausible theory that's, in my experience, sort of the real bottleneck. So we are going to see a number of models in the context of this boot camp, which do involve aspects of social context, environmental context, and where those relate to, where those serve as risk factors for, say, infection, or potentially for other common diseases. So I'm trying to think if in this particular boot camp we have an example that posits that. But yes, I mean, so that's a big draw of these sorts of models. What we are highlighting here is just some of the basics of the mechanism, but we must not get distracted from the fact that, just dealing with probabilities of transmission and so on, we're extracting away from a lot of the richness that we want to capture using these models. So, yeah.
Just the other on the kind of the same theme. So often that I think this model that was done for parts
No, I think this is a very good point, and certainly one of the, Pasteur first pointed at the importance of this issue in the closing years of the 19th century, I think, when he was dealing with and trying to understand these agents of communication, exactly how that took place, and he articulated that one of the most interesting questions is that goes beyond just understanding the pathways of infection, is what is it that leads one individual, one person, say, to be susceptible while another is not susceptible to that same agent. So even though that agent may be introduced into their environment or it'd be something they're exposed to, why is it one person gets sick and the other doesn't? And this relates very much to this issue of psychosocial stressors, the issue of risk factors, but also even at a more fundamental or more gross, sort of obvious by physical level, by medical level, but it's still an issue of underlying conditions. So, for example, with West Nile infection, there's great disparities in the level of neurological symptoms based on pre-existing conditions of the person infected, or for flu as well. Obviously, for people with weakened immune systems, those who are aged or on use of immunosuppressants. These infections present a much higher risk, and capturing that heterogeneity is absolutely key often to understanding how and why and when these infections spread in the population. Flu, of course, living in not just in Australia over the summers, but living in nursing homes and hospitals, those with weaker immune systems. Capturing that differential susceptibility is important because it may capture reservoirs of infection at times where it's not circulating in the broader population and from which it may be emerged. So we will be looking, if I make some fancy, fast footwork here, we'll be looking at a model where people start in different states of their natural history of infection at the beginning of the model, which goes partly towards addressing your question, but we could also capture with a state chart, or for that matter with a variety of other factors, different levels of susceptibility. In fact, one of the models that I've provided to you, I think, on your thumb drives, I'll get to just a sec here, is we actually have a quite articulated model of immune function at the level of an individual, and that individual is then placed in using sort of a multi-scale paradigm, that individual is placed in a social context, and that can bring them in contact with other individuals, and they can be infected by other individuals within the network, and their immune system responds to it, for example, over time in a dynamic fashion. So there we can measure, one of the big motivations for that model was to be able to quantify the impact of a heterogeneity in the population with respect to level of immunocompetence or level of immune strength, which is often an important mediator for diversity and levels of susceptible to infection. It's not the only one. I mean, there's other aspects of living conditions and so on that are also important mediators, but immunocompetence. And so we'll see if I can highlight a model like this. One of the reasons I'm encouraging questions like this, is it helps me figure out which models to feature in my discussions, and so hearing these things is really helpful. So yes. Sure. Fair enough. I welcome that sort of cautionary note, and what I will say is that one of my hopes for breaking into project teams that are working on substantive issues is that we could sort of sail between the Charybdis of trying to just hew to a pre-planned schedule, on the other hand, just trying to cater to every need in all group plenary sessions. Instead, particular project teams which substantively explore some of the texture of how you would look at vector-borne disease, how you would look at socio-behavioral factors and their impact on susceptibility or what have you, in teams that would be running in parallel. And so take everyone's time and try to devote it to one or the other of those, which the opportunity costs are prohibitive. So thank you for the comments there. I do appreciate that. One of the reasons I like to hear these things is because we have, if you look at the ODrive, there's a lot of example models there. A of example models, and I don't know which are of interest to people. And, this helps me sort of when I'm commenting on models, making sure to point to particular models. I would also note, just along those lines, that there, some of you may be interested in going and looking at the model library here. So if you go to a tiny URL, it's so you can get to this. You can get to this in different routes here, but this is one of them. You'll notice that there's an example model inventory page, which is not entirely up to date, but some of these things may strike you as of particular people here of interest, and I would be glad to, answer questions about particular models here, and in my one-on-one sessions with participants, talk about issues. So there's everything from, vector-borne illness to things with, TB risk factors, comorbidities, and some issues which involve health services delivery and immune system modeling as well. So I would suggest you might want to think about taking advantage of that. Okay, so I think we've gotten an initial glimpse here of AnyLogic. I'd like now to try to go into just a few words on some of the basics of the agent-based modeling process. I'm only going to be able to say literally a few words about that, and then we're going to go on to look at some of these mechanisms, essentially the vocabulary of agent-based modeling in greater detail.